Hello everybody, and my name is Wuyang Zong, and my topic today is a proposal of segmentation extension for RISC-V. Here's the outline today, and I will just quickly read through it. And the outline is why segmentation hardware, and new instructions for segmentation, and the benefits of segmentation, and the miscellaneous stuff related with segmentation. So why segmentation? Because segmentation can be used to create multiple protection domains on a single address space. It means that it can be used to build a single address space operating system. And traditional operating system are multiple address space operating system. And there are some drawbacks with the traditional operating system. And the benefit of single address space operating system is that first, it can reduce the context switch overhead. For the multiple address space operating system, each time when context switch happens, the operating system has to flush the TLB. And TLB flushing has been known to be a big part of the context switch overhead. So with SASOS, we no longer need to flush TLB during context switch. The second one is that data sharing is easy among processes with SASOS. You might say that in Linux or FreeBSD, you can also share data very easily by using the mmap system call. But the problem here is that the mmap system call, the problem here is that it is usually difficult to map the shared data at the same virtual address for all the processes. That means that data pointer cannot be used in the shared buffer. But with SASOS, since there's only one address space, so the shared buffer will be at a unique address, so data pointers can be used. The other benefits of segmentation are the I/O segments, physical memory segment, software managed TLB, and I'll talk about this later. And there's another one that's not shown on the slides. That's the no PIC, position independent code is needed for shared library, because each shared library has its own code segment and data segment, and all the functions and global variables are at the known location within the segment, so no PIC is needed for shared library. Okay, let's now see the segmentation hardware. In this picture, you can see that there's only one memory address space. It can be either a virtual or physical address space, depending on whether paging are supported on the platform. And each process has a capability table, and the capability table stores the list of segments that the process can access. And as you can see from this picture, even though both processes are running on a single address space, they are actually protected from each other. So capability table can create multiple protection domains on a single address space. If the process wants to share data, that's actually very simple. Operating system will just create capability for each process, and make it point to the same segment. Then the data sharing is done. Now let's look at more details about the segmentation hardware. The hardware needs to understand two data structures. The first one is the segment descriptor table. Segment descriptor table stores all the segments in the system, and to describe a segment, we only need two values. That is the base address and the length. And the segment descriptor also has some other fields. That's the generation number and attributes here. And I'll talk about this later. And the capability table, as I mentioned before, it stores the list of segments that the process has the capability to access. So each capability has three fields. The first one is an index to the segment descriptor table. The second one is also a generation number. And the third one is the permissions, such as the read, write execute permission that the process has for this segment. The generation number here is used to revoke the capability to a segment. A capability is valid only when the generation number in the capability are equal to the generation number in the segment descriptor. So if operating system want to revoke all the capabilities that point to a segment, it can simply just change the generation number in the segment descriptor. Also, there are new registers introduced with segmentation. The first one is the STR. STR point to the segment descriptor table. The second one is the CTR. CTR points to the capability table. And the third group of registers are called segment registers. And the segment register stores a segment handle. And the segment handle is actually an index into the capability table. So some of the segment registers have default usage. As you can see in the picture, the S0 segment is the default data segment, and S4 is the default stack segment, and S5 is the default code segment. Let's see other hardware for the segmentation. Besides the page TLB, the CPU will also need a segment TLB. The segment TLB is used to cache the segment descriptors. Each segment register will also have a shadow register. And the shadow register is used to cache the capability. Each time when you load a segment handle into the segment register, its corresponding capability will also loaded into the shadow register. Now let's look at the new instruction for segmentation. We need the new instruction to load or store data with segment override. The example below is a load word instruction that we want to load a data from memory that's in segment specified in the S1 register. The second group of the instruction are the instructions used to load store segment registers, because we need to save and restore the segment register during context switch. And we also have the CTR register. We also need to have instructions to load CTR register and STR register. And for share libraries, we need to have the instruction to do file call and file return. Because each share library has its own code segment, so when calling to the share library, we need to specify the segment handle of the share library. And also, when returning from the share library, we need to specify the code segment of the caller. Now let's look at the benefits of segmentation. And our first look at the benefits when on systems without paging. Segmentation can be used instead of the PMP. PMP is the mechanism defined in RISC-V privilege spec, and it can also be used to create multiple protection domains on a single address space. But I think that segmentation is more flexible, simple, and elegant. And also, segmentation will make the share library easy to implement. To implement a share library, the system should support virtual memory. Since segmentation is a kind of virtual memory, so it can make share library easy to implement. Now let's look at the benefits on systems that support paging. As I mentioned earlier, that each segment can have some attributes. And here the L segment is actually the attribute of a segment. This attribute will change the way that the address is translated. Normally when we do the address translation, the segment address here is actually means that the segment address here is actually a segment handle plus a effective address. So with the IO segment, normally the segment address is translated to virtual address through segmentation and then translated to physical address through paging. But with the IO segment, the segment address is translated directly to IO address. So the benefit of this is that the node page TLB entry is needed for device driver to access its hardware device. The second benefit of this attribute is that we only need one set of load store instructions to load or store data from either memory or I/O. The second benefit on systems with paging is also an attribute called physical memory segment. And physical memory segment can improve the performance of big memory workloads. And there's a paper published in RISC-V in 2013. In this paper, they proposed a concept called direct segment. And direct segment is used to map a region of virtual memory directly to physical memory. And by doing so, it can improve the performance of some applications with big memory workloads. And since physical memory segment has the same effect as direct segment, so it will have the same result as direct segment. Now let's see the software managed TLB. For a system to segmentation can make the software TLB possible. To build a software managed TLB, the prerequisite is that segment or page TLB miss cannot happen during TLB mishandling. So how can we guarantee that? We can guarantee that by making kernel code data and stack segment as physical memory segment, and by making kernel code data and stack segment descriptors always resident in TLB. Then we can guarantee that TLB miss will not happen during TLB mishandling. Now, the miscellaneous stuff related with the segmentation. First, we'll see that with segmentation, the stack growth direction should be upwards. And if the stack grows downwards, as shown on the left-hand side of the picture, when stack pointer reaches 0, there's no way to expand the stack segment. But if the stack grows upwards, as shown on the right-hand side of the picture, when the stack pointer reaches the maximum segment length, there's still a good chance to expand the stack segment by moving the stack segment to other location with large enough free space, and then set the new length for the stack segment. All of above are all about the hardware side for the segmentation. And at the software side, that compiler support is needed because compiler needs to support file code or data point. Also, new way to link shared libraries is needed. And on the OS side, that the OS need to change from multiple address space architecture to single address space architecture. So that's all I have for this presentation. Thanks.
Did you do any analysis on the overhead of this new extension?
No, not yet. This is just at the proposal stage.
I'm curious that you say you can use the segmentation TLB to, I guess, for speed up. Does that mean that in worst case of your design will have the real-time memory access, which the OTS TLB and fetch table are TLBs?
You are talking about the segment TLB. Okay. TLB is actually a cache for address translation, and since segmentation is also a kind of address translation, so the CPU need to cache this address translation.